Hi, my name is Justin Arroyo. I am a CVN student and I work full-time at Pratt & Whitney's Jet Engine Assembly Center in Connecticut. As such, I decided to do my final project on jet engines and aircraft. So commercial aviation is currently powered by carbon dioxide emitting fuels like kerosene, and emission-free fuel sources are going to be required in the future to prevent continued global warming. And ammonia is one promising carbon-free energy source, but it isn't really used in jet engines because of its poor combustion characteristics. However, recently Pratt & Whitney, uh, a large commercial jet engine manufacturer, patented an ammonia-powered engine design, the schematic of which is shown here, which attempts to address ammonia's combustion problems by passing the ammonia through a cracker, which is highlighted in this red box, converting it into nitrogen and hydrogen per the equation also shown on the slide, so that the hydrogen and the ammonia co-fire in the combustor, increasing the combustion performance. So to assess the feasibility of this concept, I looked at three things: the equilibrium ammonia conversion, the cracker sizing, and thermal requirements, and then the nitrous oxide emissions as a result to see if we're actually even helping to abate greenhouse gases. So the way these three parts of the question were addressed is, so to start with the equilibrium ammonia conversion, this was just simply calculating the extent of the reaction as a function of temperature and pressure. The temperature captured through this equilibrium constant K, which is mainly just a function of the different species parameters or characteristics. And then to factor in the pressure, you have to calculate, that pressure ratio, which you can see in equation 2 there, but also the effects of fugacity, which is basically capturing the non-ideal behaviors of the gases in the solution. And to do that, I used the equations 3 and 4, the compressibility factor driven estimation of fugacity. For the cracker sizing, I used a simplified form of the ammonia decomposition rate equation, and then I plugged that into a typical plug flow reactor design equation to get, and I just solved that using a numerical integration method. And then to estimate the ammonia flow rate, I used facts about up the plane, the E195E2 jet, in combination with kerosene characteristics and then ammonia characteristics to estimate a molar and volumetric flow rate to get thermal management and the volume of the cracker. And then lastly, for nitrous oxide emissions, I used a very similar method to what we get done in our most recent homework. To comment on the success of the models, the equilibrium NH3 conversion was, well, I would say, generally successful. Error did increase at higher pressures and lower temperatures, probably because of the fugacity estimation method. The method I used using compressibility factor was very old. Modern methods use a second virial coefficient, which requires a lot more data that I'm sure Pratt & Whitney had access to, but I simply did not. And then the cracker, and the thermal management, honestly, a lot of the assumptions are actually pretty huge. Like a plug flow reactor really is not the right reactor I should have chosen. I should have chosen a catalyzed packed bed reactor, which factors in how the volume of the catalyst and the pressure drop over the catalyst and the partial pressure of the gases being absorbed and deabsorbed by the catalyst. But I, just went for the plug flow reactor to keep it simple and feasible for me to do this by myself. And then you can see just other listed assumptions here, like the flow rate using, kind of back of the napkin calculations. And then also realistically, the fuel won't be coming into the cracker at standard temperature and pressure, which is what I assumed for this. It'd be pre-treated before. So the thermal requirements might ended up being better than what I calculated it as. At least I would hope. You'll see when I get there. And then lastly, for the nitrous oxide emissions, a big simplification to only consider nitrous monoxide and not the other nitrous oxides. You saw in the model, I didn't include the pressure effect to the way entropy changes. And when this is kind of a big deal because the combustion is going on in a jet engine combustor, which could have a pressure ratio of 30 or 40 or 50 to 1 to atmospheric pressure. And I also wasn't very particular about the excess air that was supplied, the equivalence ratios, because ultimately it turned out that the thermodynamics of nitrous oxide emissions are not that interesting for ammonia combustion, and I'll explain that in the next slide, or the next couple slides. So these are the three most interesting plots that came out of the model. Just to briefly touch on the three of them before getting into the discussion. The equilibrium NH3 conversion, is a pretty clear demonstration of Le Chatelier's principle, where we have an endothermic reaction where conversion favors the products at higher temperatures. Then we also have a reaction where there are more moles on the right-hand side than the left-hand side. So as the pressure increases, it wants to push the reaction towards the left-hand side, which is ammonia in this case. And then the reactor volume and heat transfer required, you can basically see that the reactor volume is simply, it's pretty large. Like I had to cut the graph off at 1,000 for a temperature of 400 degrees C. And the temperature has a huge effect on the reactor volume, so which is a bit unfortunate because the higher temperatures are just tough to achieve. This is captured by the Arrhenius equation on the model slide. But I'll discuss why that's a challenge on the next slide. And then the normalized G over moles of Na, the y-axis has no label because this is just normalized G values that don't really mean anything. And you can kind of see that per 4 moles of ammonia entering, we only have 0.01 moles-ish coming out, so it ends up being less than 1% of the combustion products are nitrous monoxide. So when looking at the results, when looking at the equilibrium ammonia conversion, you must first acknowledge the fact that while you would love to have it as low pressure as possible, you must have it at some higher pressure because the ammonia must flow through the fuel circuit and through the packed bed reactor. The patent looked at 400 psi A and 4000 psi A, and I speculate this because 400 psi A is probably as low as you could go, and while still having the ammonia go through the circuit, and then 4000 psi A is a pretty typical fuel pressure before entering the combustor. So an implementation for this could be pump the ammonia up to 400 psi, run it through the cracker, and then have the cracked ammonia hydrogen mixture then go through another round of pumping to 4000 psi before being fed into the combustor. And then 600 degrees C is obviously better than 400 degrees C because that's just how endothermic reactions work for when you were trying to skew equilibrium one way or the other. But 600 degrees C is just extremely tough for these commercial engines because 600 degrees just would have to come from the hot section of the engine. You don't get that from the oil, you don't get that from the compressor air, and you kind of want that hot engine air, which is in limited supply on these high bypass turbofans, to go towards driving the engine and not towards heating up your fuel. But when you look at the cracker, moving on to the cracker sizing, you run into the same operating set point dilemma where having it be at a higher temperature is just so much better. And if you look at how ammonia decomposition happens for hydrogen fuel cells, those are running at 800, 900 degrees Celsius. So it makes sense that 600 degrees Celsius would be kind of a minimum, and 400 degrees Celsius is really just going way too low. But that might not even be your biggest problem, because if you saw the axis on the graph on the previous slide, the thermal requirements are in the megawatts, which is like the size of a solar farm. So once again, like there's lots of hot air in an engine, but that might just be too much. And then lastly, the nitrous oxide emissions. From a thermal perspective, it's honestly just uninteresting. The main challenge is that NH3, as it combusts, forms these radicals that like to bond with oxygen to form nitrogen monoxide. So it's really more of a combustion pathway thing, a kinetics thing, than it is a thermodynamics thing. So to summarize, I have all the key findings on the screen with what looks good on the left and then what could be done in the future on the right. So what was good are basically the equilibriums. Thermodynamics is not the limiting factor for the ammonia conversion, and reasonable engine operating conditions would lead to good ammonia conversions in infinite time. And in theory, we'd have low nitrous oxide emissions too, based on equilibriums. But the bad part is that cracking ammonia is highly endothermic. So really, this analysis should have been done with a smaller plane, and that should be looked more closely into next time with fewer assumptions. And then lastly, the kinetics look bad. There could be new catalysts, new combustor designs, new exhaust treatment, but I won't focus on that too much because this is the thermodynamics class. That was my project. Thank you for listening.